Hi, I'm Sam Garrett, and this is some work of mine with John Chalker, which appeared in Physical Review B in January. Goldstone modes in the emergent gauge fields of a frustrated magnet. I'll start by talking about what is arguably the most well-known frustrated magnet, spin ice. Let's fill space with these corner-sharing tetrahedra pictured on the left. In spin ice, you have spins on the corners of these tetrahedra pointing either in or out. The ground states then have 2 spins pointing in and 2 spins pointing out of each tetrahedron. This model is actually equivalent to the easing antiferromagnet on the same lattice. But also, clearly the requirement that 2 spins pointing in and 2 out of each tetrahedron is not going to uniquely constrain the spin configuration, and so there's a huge ground state degeneracy. Now there's an elegant way to describe all of these ground states. Looking at a spin ice configuration, if we interpret the spins as fluxes into or out of a tetrahedron, you see that we could think of the spin configuration as a divergenceless vector field. This vector field can then be described, just as in electromagnetism, as the curl of a gauge field. Also, this gauge field structure implies intricate correlations between the spins, which show up in neutron scattering. So this is the spin-flip neutron scattering on the spin ice material holmium titanate. Now this spin ice has arisen because spins have been forced to lie along certain axes in the pyroclore lattice. Without this anisotropy, we might want to think about the Heisenberg model on the pyroclore lattice. So let's keep it classical. These spins are now 3 component vectors, and I'll restrict here to nearest neighbor interactions. In ground states, each of the components of the spins maps to a divergenceless vector field, and consequently they're labeled by not 1 but 3 emergent gauge fields. Again, all of the gauge field configurations are ground states. This model also has a natural dynamics, coming from the precession of the spins in the exchange fields of their neighbors. There are a large number of zero modes as well, arising from fluctuations of the gauge fields. These correspond to smooth deformations of the ground state. However, because of these soft fluctuations, the model is very sensitive to perturbations. For example, in the spin liquid NCNF, we expect disorder in the locations of non-magnetic ions, and consequently also disorder in the exchange interactions. But if rotational symmetry is not broken, we might then consider the classical Hamiltonian here. Here delta is characterizing the width of the distribution of exchange interactions. We're going to think about this as a weak perturbation. With this disorder, we expect a particular ground state to be selected. Previous studies have shown that this gives rise to a spin glass transition at a temperature of order delta. Below this, we have freezing of the gauge fields, and therefore a spontaneous breaking of the global rotational symmetry. We expect Goldstone modes. This ground state freezing also gives us a controlled way to study the low energy dynamics. After finding a ground state, we can perturb around it and use harmonic spin wave theory. Without disorder, there are many zero modes. Now we find that our lowest modes have frequencies of order delta. And this implies that they're related to the gauge fields, with some interesting subtleties that unfortunately I won't have time to talk about. On the right here, we show the integrated mode density as a function of the mode frequency scaled by the disorder strength. And the legend here indicates delta. If these gauge field fluctuations are Goldstone modes, they must be associated with smooth twists of the ground state configuration. We can look at how the spins fluctuate in these modes, and correlations between the local rotation angles, which here I've labeled by theta. Now in our lowest modes, we see on the right that we have an effective wavelength scaling with the system length. These gauge modes are therefore Goldstone modes. So what do? We develop a hydrodynamic theory of the Goldstone modes, working with a coarse-grained magnetization density and a vector field describing the rotations. We determine the equations of motion describing low-energy spin waves in the pyroclore spin glass. Looking at the second of our equations here, we see that the response of the magnetization to the twist is extremely weak. And this is arising from the low-energy gauge field fluctuations. This result is not captured by the conventional Halperin-Saslow theory of spin waves. Now, taking our equation of motion, we find linearly dispersing Goldstone modes. Strikingly, the spin wave speed is actually independent of the average exchange interaction. It only depends on the randomness. This is to be compared with the result of conventional Halperin-Saslow theory, which predicts a spin wave speed depending on the square root of the product of the average exchange and the magnitude of the randomness, the latter characterizing the so-called spin wave stiffness. Now this linear dispersion gives rise to a dramatic power law increase of the magnetic heat capacity as temperature is increased. This behavior has actually recently been observed in the spin liquid material NCNF, which I mentioned before. The observed power there is slightly lower, but we do expect our results to apply in the low temperature limit, and there is some clear curvature in the data. This brings me to the conclusions. We have developed a hydrodynamic theory of spin waves, highlighting a modification of the Halper and Saslow theory, which arises due to the abundant soft fluctuations typical of frustrated magnets. The Goldstone modes we find are related to fluctuations of the emergent gauge fields, with a speed which, amazingly, doesn't depend on the average exchange interaction. We also point out that these modes should give rise to a power law dependence of the heat capacity on temperature, rising extremely quickly in the limit of weak disorder. And this is exactly what's recently been observed in NCNF. Thanks for listening.